Okay, hello. We are here. This is our first video, our first flip classroom video of the semester. You're welcome. I hope you enjoy it. I hope you already talked about your weekends. If you haven't, pause the video, go talk about them our end, please. Our goal is today we're going to graph log functions and we're going to convert to exponential form. Song of the day is Millionaire by Chris Stapleton. I figured I'd go with the country theme since I will be in Nashville. You know, I just feel like a millionaire every single day. I just make millions. Not so much. I mean, that's just. I mean, okay. Anyway, so let's talk to it. Okay, so let's talk about it. Let's sketch a graph of b to the x. Well, remember every single time we do these functions, all right, we have our key points 0, comma 1 and 1, comma b. All right, and y equals 0 key features. Let's pretend this is 3dx, so this would be 1, comma 3 actually. Here's my quick sketch, 1, comma 3. There's a reason we're doing this. All right, I know that didn't go through 1, comma 3. I'm also using my finger right now to write. It's pretty tough, so you're gonna have to battle. We're gonna have to deal with it. I'm sorry, I apologize. Here we go. So after today, yes, of course. Now, wow. Now we want to think of now we want to talk about logs. All right, logs and exponentials are related because they're inverse functions. All right, so if I graph my exponential function at 0, 1, and 1, let's pretend it's 1, comma 3, remember? All right, my exponential function will look like this. Okay, and I have that asymptote. Well, if I'm going to pretend I'm sketching log, stay consistent, I'll make my base 3. Any inverse functions, they're going to reflect over a dotted line, okay? And the dotted line that they reflect over is the graph y equals x, all right? Now remember that when we were talking about inverses during our first unit, okay, we had these ordered pairs, and we had ordered pairs 0, comma 1 and 1, comma 3. Well, to make those things inverses of each other, the inverse of 0, comma 1, what did I do? I switched my x and y values. That was from our first unit. So to plot my log base 3 of x, I switch my x and y values 1, comma 0 and 3, comma 1. Now that's a terrible dot, but we're going to battle. Remember that our asymptote for our horizontal asymptote was y equals 0. Well, again, I switch y with x, so now I'm going to have a vertical asymptote at x equals 0. I'm not going to include that here just because I already have that graph on there. So my log function, what's America? Looks like something like that. Again, that's a rough sketch. Okay, but the biggest thing is that we recognize that they're inverse operations or inverse functions. Look at that, how they reflect over that line. All right. So what does it all mean? Well, we just wrote down these key features. Okay, we just wrote down the key features: 1, comma 0, or excuse me, 0, comma 1, 0, 1, and 1, comma b. So on our key features here will be 1, comma 0, and b, comma 1. All right, like I said, if I have y equals 0, I'll have a vertical asymptote of x equals 0. Biggest thing when we ask ourselves when we're solving log equations, logarithmic expressions, where did that picture is? Sorry, when solving logarithmic, yep. I'm just going to stop there. What power? What power? What power of 5 gives me 25? The second. Okay. This is an example of the exponential function. This is what the logarithmic function would look like. 5, I call this circle of life, remember? 5 to the second gave me 25. What power? What power of my base? My base is 5, will give me 25. Okay, again, what power? It's capitalized. Got to be important. Use a definition to evaluate. Evaluate means we're going to get a value or a number. for x. Okay, I want to evaluate the following functions. So what does this mean? F of x equals a log base 4 of x. So use this definition to evaluate when x equals 16. I'm going to find f of 16 equal log base 4. Well, since x is 16, I'm going to make this a 16. So what power of 4 will give me 16? Oh, 4 to the second. 4 to the question mark equals 16 for the x. Oh, it's 2. What power of 2 gives me 64? Oh, it's 6. 5 to what power gives me 1? 5, the question marker to the x equals 1. What power of 5 gives me 1? Well, anything to the 0 power, sorry, it shouldn't be x, it should be question mark. Anything to the 0 power is 1. So my answer is actually 0 here. Remember that. Anything to the power of 0 is 1. Okay? 3 to what power gives me 1 over 81? Remember what I said yesterday, that anytime we have fractions, okay, that means I had a negative exponent. Because 81 can be expressed as 3 to the 4th power. All right, well, 81 can be expressed as 3 to the 4th power. If I have 1 over 81, that means my answer should be negative 4. Because if I flip this up to the top, remember if we flip, we have to change the sign of the exponent. So the biggest question, if you see something like this, think to yourself, what power of this base will give me this answer? What power of 5 will give me 1? 4 to what power will give me 2? 3 to what power will give me 1 over 81? Wow, that's bad. All right, cool. Sick, here we go. So remember, this says okay, now we're writing the logarithmic equation as exponential equation, then solve for y. Okay, so this is essentially what power of 2 gives me 16. Before I can do that, I have to write this as an exponential equation. Well, this is where the circle of life comes in. Okay, 2 is the base, so 2 is the base. 2 to the y gives me 16. 2 to what power gives me 16? 2 to the y, well, I know that is 2 to the 4th. Remember from yesterday, these bases cancel out, so y is 4. 2 to what power gives me 1/2. Oh, 2 to the first power gives me 2. So this must be 2 to the negative 1, because there's a 2 on the bottom that can be considered as 2 to the negative first power, so y is negative 1. Oh my gosh. Okay. Wow, this is going to be a fun one. Y, the 5th, is 17. Well, can I raise anything to the 5th power and get 17? No. But if I were to solve for y, I would take the 5th root of both sides. If this were y squared, I take the square root. For y to the 3rd, I take the cube root. But we have the 5th root, so I take the 5th root of both sides. These cancel out. So y is the 5th root of 17. Okay. Some log properties for us. Properties of logs. Here we go. If you see anything, any base, and I have a 1 here, anything to the 0 power gives me 1. So b to what power will give me 1? Every single time, it'll be 0. Okay. If I have the log base b of b, well, if these two numbers match, like if it was the log base 3 of 3, it's just 1. Here's the log base b of b. Well, this we know, I know that this right here is 1. Okay. So this, it's like 1 times x, which is x. If I raise an exponent, so I have here's my exponent. If I have a log in my exponent with the same base as my original base, these cancel out, and I'm left over with x. If I have the log base b of x equal to log base b of y, well, if these are the same bases, then I can set these equal. These are all general cases that we're going to apply later on to some problem. All right. Is there a log that perhaps appears more commonly than others? Yeah, there is. Okay, like if I were to solve for a value of a log on my calculator, the calculator is automatically in base 10. So we just write it as log. Anytime you see this, okay, I'm going to assume its base is 10. If it just says the log of, I don't know, 100, I can assume that's the log base 10 of 100. Mathematicians can be lazy at times, all right, so that's why this happens. Okay, we just assume that it's 10. And I know you're not supposed to assume, but I'm going to tell you that if you just see a log, the rule is to know that it is base 10. Okay, what about one with a more natural base? Well, if I take the log of this e is an exponential function, okay, e is like 2 point something, 2.456, blah, 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 blah. All right, well, we don't take the log base e, we use the natural log to evaluate things to the power of e to some power, okay, because the base of the natural log is e. Oops. This says base e, which is about 2.718. That's a 2, not a z. Next page. Let's flip it. All right, we're going kind of fast. 10 to what power gives me 100? 2. 10 to what power gives me 2/5? Well, here's the deal. All right, I can plug this into my calculator. I can take the log of 2 over 5 in my calculator, and I'll get negative 0.398. Same thing here. I can take the log. If I don't know what this is, 10 to what power gives me 5? There is no power of 10 to get 5. So if that's the case, plug it in. Plug it in. Okay. I'm going to plug in, I get 0.699 by plugging the log of 5. 10 to what power gives me negative 4? No power. Okay, because if I plug this into my calculator, the log of negative 4, I'll get an error. Because the domain of our log functions are from 0 to infinity. Remember back on the first slide when we talked about our vertical asymptotes back here? A vertical asymptote's at x equals 0. That means in my parent function, I do not include any negative numbers. ln of 4. E to what power gives me 4? E to some power gives me 4. I don't know. So I'll plug this into my calculator. It's right underneath the log button. All right. The log button's on your left-hand side of your calculator. ln of 1, well, that's still 0. E to what power gives me whatever. I'm going to pause, and I'm going to show you the answers. All right, first, your homework are the odds. Second, here we go. How do I find inverses? I switch my x and y values, which means my domain and range is switched. Find the relationship reflect over y equals x. Why can't it be negative? Because I have an asymptote. Domain of a basic log is 0 to infinity. The range is negative infinity to infinity. Holy